So I will go to the second part. So let's start with some details on the energy grid. So this school should be mainly dedicated on this. So I would like to have this introduction, so you will have more details in the next talks, in the next lectures, next days. But as we already have listened yesterday, normally the energy grid, the power grid are, I would say, are organized in a centralized way. So you have a big power plant, and then there is transmission, okay, where there is, in the power plant there is the generation of energy, then there is the transmission part, and then the distribution through the households, for example. So it's really centralized, and there is just a unicast distribution, I would say. So there is from the power plant to the customers, okay? So in this architecture, they have identified that there are a lot of wastage. In every part, they waste energy, in the generation, and mainly in the transmission and in the distribution. So because of the difficulties in the energy market, they want to decrease these losses that they have in order to have more efficient power grids. So this is the first thing. The second is that mainly the power plants are based on fossil fuels, so carbon or petrol or whatever, and this is not exactly the way that we want to go if we are following a more sustainable future according to the manifesto of the European Commission, and we can open a long discussion on this, but this is the way we should go. And also, as in our mobile networks, even in the power grids, the plants are sized for the peak. And then most of the time you don't need a peak. So there is, again, if you are not managing in a proper way, there is some losses there. And also another thing is that currently there is not much done on the energy storage in the power plant and in the power grids in general. So what has been studying is to have more distributed generation, for example using renewable small-scale sources like in this picture, so you may have some solar panel installed in your roof or some solar garden, let's say. The problem is that, again, as already introduced in our domain in energy sustainable mobile network, these distributed generators alters the nature of the grid, which is not anymore centralized, it's distributed. So much more interactions is needed when you are following this new distributed paradigm. This is the reason why they are opening a new research field that is called smart grid, because they want to control this distributed system in a self-optimized way. So it's important here to highlight self. So again, automation is important in this part, as in our networks. And also they want bidirectional energy flows, because I have distributed generators. So one generator may have to distribute the energy to a customer, and may also want to receive energy from another distributed generator in a given point of time. To make this, they need bidirectional communication. This is the reason why they put smart everything in everywhere, because smart is kind of acronym to say that you are using communication to make something that is more intelligent. So, because why they want to use communication? Because since you may want to give your energy to another customer, to receive energy, you need some communication between the different entities. Then you want to supply the demand of energy that you may have in a given point of the network, and you may also want to incentivize the user to reduce the power demand. And in this case, there is also a bidirectional money flows, because there is a lot of work that is going on the trading, the energy trading of this part. So, for example, one good example is that the operator are trying to have different prices at a different time of the day in order to incentivize the user to use some facilities in a given hour, which is not the peak for the power plant. So this is the idea of these bidirectional money flows. So now I want to introduce some entities that are used in the smart grid. The first one, I already referred to this when I was talking, is called prosumer, which is actually a word that is divided into producer and consumer. So the idea is exactly as I said before. So there is an house that has a power plant. So the house is producing energy because of the solar panel that I installed, but it's also consuming energy because of the facilities that are inside the power plant, inside the house. Then there is this other concept that is the microgrid, which is actually a subsection of the network with distributed generation and maybe storage. Normally it's low or medium voltage, it's not high voltage as the big power plant that we have or we had in the past. It tends to be independent as much as we can from the big grid, the microgrid, in order to have like a net zero operation or not to import any energy from the big grid. And then there is this other concept that is called virtual power plant, which is a cluster of microgrid actually that are controlled by a single entity. Tomorrow I think we will have a talk on this, because all this field is also referred to Internet of Energy. So we will see more details tomorrow about this. So this is really interesting because I think it's a really cross-disciplinary field between networking and smart grid. So it will be interesting to listen to the talk tomorrow. So some functions. I reported here two main functions from the smart grid. The first one is called supply load control. That is the process to provide the sufficient energy to satisfy the demand. So imagine that you have a power plant with heterogeneous sources, some renewable, some not, and then you decide from which energy source you have to take the energy, and maybe you have to switch on some more power plant if there is a peak demand. And then another function that is really important, we will see later, for our purpose is demand response, which is the process to equalize the load when I have a limited available capacity. So, to give some example, one thing is to have what is called direct load control. So actually switch off some facility that is not needed for a given point of time because I do not have energy. So I decide to switch off that facility. Or another one is load shifting. Load shifting is about to shift the load to a different time. For example, if I am in my house and I want to use my washing machine, then the operator may want to incentivize me, let's say, to use the washing machine in a different time because at noon, for example, there is a peak, so it doesn't allow me to use the washing machine. And this may be done brute force, so the washing machine is not switching on, or may be done through what is called gamification. So the idea is that you have a smart pricing process. So if you are using washing machine during the evening, you are paying less. So you are incentivized to use the washing machine in a different point of time. And this is the picture that is summarizing all the things that I'm introducing. This is taken from this paper, from Cutitas and Tasciulas. So you can look at this house is a prosumer because it's consuming energy inside and is producing energy with the solar panel. This is a simple house, which is a simple customer, is not producing energy. And all this block, this set of houses is a microgrid. This is another microgrid. These are controlled by this entity here. So they are constituting a virtual power plant. And you can also notice that each prosumer and consumer has an agent and this aggregator in order to have some communication and to make all the functionalities that I introduced before, like for example demand response. And also we will have always our power plant here because we are not completely self-sustainable, so maybe we may want to have some power, some energy from the big energy grid. And also I want to highlight that all these links are communication links, and of course there are electrical links between the power plant and the households, and these links should be bidirectional, both from communication and electrical perspective. So the energy and the data are flowing in both directions. So let's now move to our case. So what you are doing here is, I would maintain this term SMART, but actually is what I called before energy sustainable mobile architecture. And we have different entities that are playing the game in this scenario. So we have macro cells that are probably only coverage base station. For example, they can use massive MIMO to decrease the energy consumption. And they are providing global coverage to our users. And they are normally deployed in a very detailed and planned way. So the operator may want to put the base station exactly in a given point in the space. And then there are other smaller base stations like microcells, picocells, or femtocell. Normally femtocell are within the buildings that are more for capacity purposes, deployed for capacity purposes. They are normally, they may want to have like plug and play installation, so they don't want to have any planning strategy to deploy this smaller base station. And they are referring to self-organization for organize and configure, optimize these types of base station, and may also have some intelligent control for energy management, like for example some functionalities such as the demand response or the direct control load, for example, under on-off screens. All this architecture can be also extended to data centers. So I'm not referring to this. There is again an active literature of this. So there are data centers that are supplied with renewable energy sources, and there is a lot of studies. I also aware about another European training network that is working on this. It's called Big Storage. So if you want to refer to the most recent literature, look at the website of these guys. They are working on these topics. So again, if we are using the terminology of smart grid, we can define the mobile microgrid, which is a portion of our mobile networks that is supplied by distributed generation, by renewable energy sources. And this portion of the network, this distributed sources might or may not be directly connected to the base station. So this generator could be embedded in a base station or could be deployed in a different zone. And of course, what we want is self-organized control of the energy for macro and small base stations. So in this case, our prosumer are the base stations. So the base station is consuming energy because it's serving some users, but it's also producing energy because it has the solar panel or whatever other kind of energy harvester you can have. And in the case of data centers, in the case that you are supplying data center with renewable energy, again, the data center can be seen as a prosumer. And then the most important thing for us is mobile network demand response. So what we want to do is to equalize the aggregated load, taking into account the available energy capacity that is given to me by the energy harvester that I've deployed in the portion of the network that I want to control. And the idea of this is to operate in what is called island mode. So let's say to be off the grid, so to be self-sustainable and to not rely on the big energy grid. So the idea here is not, as in the energy efficient part, to make the power consumption of the network proportional to the traffic load, but is to make the power consumption of the network proportional to the available capacity of the harvester that I have in the network. So it's a bit of paradigm shift with respect to energy efficiency. But I would say that energy efficient is part of this game. In fact, thanks to Angel and Nicola for this picture, we can include energy efficiency within this big picture of what I've described. In fact, if I want self-sustainability of a given portion of the network, for example, microgrid with some small cell in the coverage area of this microgrid, for sure I have to start with have some energy efficient technique in order to reduce the power consumption of the network. And I can rely also for the device part, for example, on functionalities like sub foraging. So I will offload some computational capacity to some external computational entity that is executing some tasks in order to save the battery of this low power device. And also I can have some energy cooperation among the different entities, so they can share, for example, energy. So if this portion of the network has, for a given reason, more energy than the other, they may want to transfer part of the energy to the other section of the network in order to be self-sustainable. And the other idea is also to interact with the big smart grid, and maybe in this game some money flow is also acting a good role, because probably when you buy energy you have to pay something, but maybe when you are selling energy you can make some profit on the energy that you are selling. Okay, so with this I conclude the second part of the presentation, and now I want to describe and to introduce some examples on how to control this network that I introduced before. So I will report here the optimization problem that we have. So what we want is to optimize, and then we will see what optimize could be. The use of the available energy budget that I have from the energy harvesters that I've deployed. Try to avoiding any service interruption or degradation in our system. And to have this, I have to deal mainly with two random processes, which are traffic demands and energy arrival. So in what follows, I will first try to statistically describe these two processes. So I will start with the energy part, and I will refer to the solar energy, which is one of the most used energy in the world, and I would refer to the photovoltaic panel. So this is a scheme, the classical scheme of a photovoltaic panel that we have. So this is the panel itself, that we have a power processor, we may have an energy buffer or not, and then this is the load that in our case is a base station, but can be whatever device you want to put, for example, a sensor or a mobile terminal or whatever you want. So let's try to characterize these different parts of the network of this harvester. So the first part is the photovoltaic panel, and to understand how it works and the current that is generating for the rest of the system, I have to refer to the astronomical model, because actually the harvester is capturing the solar radiance and is transforming into current. And this current is depending on different parameters, like the location of the solar panel, so where it's located, longitude and latitude, the inclination, the season of the year, and the time of the day. And then based on this, I can have the current that is generated by the photovoltaic panel. How can I have this information? In our case, we are lucky. It's not, as Lorenza said, for traffic data. There are some online available databases. In what follows, I refer to this database that is for United States and is completely giving some information on this current per hour basis in many zones in United States. But there are other databases that are referring more to Europe if you want to be more on the site where you are located. Then how it works, the photovoltaic panel. Actually, the photovoltaic panel is a set of solar cells. And these cells are characterized by this current voltage curve that is actually describing the behavior of the cells itself. And through this curve, I can model actually the solar panel, taking into account the number of solar cells that are deployed in the panel. So the size actually of the solar panel itself. Then there is another important part, that is the power processor. The guys from INREL and Power probably have more knowledge of me of this part, but actually what is doing this processor here is to stabilize the current at the load and to maximize the power transfer between the solar panel, the photovoltaic panel, and the load itself. So this is the idea of this power processor here. And then based on this characterization, together with Marco, Michele, and some colleagues in Padua, we try to structure a Markov chain to characterize the amount of energy that is produced by a solar panel in a given zone of our planet. So in this case, we use a semi-Markov model. So we have Markov chain with NS states. With NS could be higher than 2 because less is not useful. And then this semi-Markov because we are the system is evolving in cycle. So when we are in a given instant of time and k, for example, the state is giving to us the current that is produced by the solar power to the load, and is governed by this PDF. Let's call G. Then after tau k, the system is evolving, is in jumping to the state k plus 1, and this transition probability is governed by this other PDF, probability density function F, that we have characterized based on the database that we have available by this National Research Laboratory in US. And what we have done is to study two different clustering. So the first one is the simple with ns equal to 2. So night-day clustering. So we have day and night. So these are the two states of the Markov chain. And then another that is more based on slot-based clustering. So we have more level of intensity during the day and during the night of the current produced by the photovoltaic panels. And these are the results that we have. So these are the case of night-day clustering, and this is for 12 slot clustering. And we can say that already with two states we have a good approximation, as you can see in this graph that is showing the second order statistics of the model, referring to the database, so to the empirical data that we have. But if you want more accuracy, we need 12 slots to have a very good accuracy of the model. But what I wanted to stress in this slide is not the result of our investigation itself, but the variability of the solar energy. So in this graph, you have the PDF of the current that is delivered to the load over the 24 hours of a day. And you can see that there is a kind of a bell shape that is centered around noon, but there is a high variability. So for the same day, you can have a very high current, but also very low current for the load. So we have variability in the amplitude, but also the shape can change according to the season of the year. So in this case, this is the column CDF of the duration of the day for different months. And for example, this is the case of December, and you can see that we are more or less around 9 hours of daylight. And then if we are going to July and February and July, the daylight is increasing. So what I'm saying is that this bell is also having a different shape. So these things is also increasing. So we have to take into account all this variability when we design our networks. So let's pass to the second environmental variability. That is about traffic. We have already some discussion on this during the Lorenza's presentation this morning. So in our case, traffic is what is producing the load. So the base station wants to serve the users, and then is consuming energy to serve traffic to the users. And the traffic is highly variable because it's generated by different services and different applications. So the traffic can have different packet distribution over the time, and can be also generated by heterogeneous devices. So we have mobile phones for human type communication, but we have machine for machine type communication or sensor nodes that are completely different traffic characterizations. And also the user may have different distribution in different zone of the network, may move through the network, through different base stations, and may have different density, for example, because there are different population density in a given zone that I want to cover with my network. So we have to characterize the traffic in time and space. So these are the two dimensions that I have to take into account when I characterize and modeling the traffic. And for this, we already discussed this morning, if we could have some available data, would be fine. But we don't. Or we have partial information from some literature or some databases that we have available. So the most used temporal behavior for a traffic is the one introduced by this project, the Earth project. Was in 2000, it ended in 2013, if I remember correctly. And they say that this is the normal traffic profile of LTE base station. and probably they are referring to some data sets available from the operator called Docomo. But we don't know more than this. So this is a kind of not really detailed representation of the traffic, and it's only on time, it's not on space. So we don't have any information how the users are distributed in a given zone. So this is one thing that we have to take into account. Then another important information that we have is by this guy here. They have done an intensive study and data analytics in Hong Kong. They have access to more or less 10,000 towers in Hong Kong there. And they report in this paper, you can surf the web and look at this paper, that they have this figure here. So they are reporting here the traffic in a day, in the 24 hours, the traffic in a week, and then the traffic in a month. And you can see that there is a strong correlation between the traffic intensity and the human activity. So actually during night the traffic is very low, and then the peaks, so there is this double hump here. So the very big peak is around lunchtime, and then there is another around dinner. Then we have a decrease in behavior here. And then they also make some estimation about how the traffic is varying during the week. And they say that during the weekends the traffic is a bit decreasing, not much, but it's decreasing. And also there is some information about how varying in the different weeks of the month. So this is the average of all the data set that they have. And also they are providing some information about the space distribution of the traffic. So the color is referring to the different traffic intensity, and the different picture here are referring to different time of the day. So this is early morning, and you can see that there are all the zones that are in blue, and some zones that are a bit more traffic. Then the traffic is increasing in this central zone, increasing, and then decreasing again. So what we can say on top of this is that there are some zones that are really following this behavior. So they are increasing traffic during the day, and they are decreasing again. But there are other zones in which this behavior is much less intensive. So when I want to control and optimize the network, I may want to take into account where the base station that I want to supply with my energy harvester is deployed, because the traffic could be really different. And this is just for a portion of the city of Hong Kong. So since they have looked at this problem, they try to clusterize the traffic behavior in different areas of the city, and they, through some algorithm, they have identified 5 regions for all the data set that they have. The first one is they call resident area, when they have this journal behavior and this behavior for all the week. Another one is transport area, and then office, entertainment, and comprehensive area. So you can see that the shape is really different from one area to the other. So for example, this first is in a residential area. The very big peak is at the evening, when probably people are coming back to their houses, and they are starting having some communication, surfing the web. Well, in the transport area, we can notice that there are 2 peaks. Probably is the peaks are correlated to the time of the day when the people are going to the work and coming back, and then other different behavior for different areas. And also it's important to notice that, for example, in residential area, there is no difference between a weekday and the weekend. While in the case of transport and office area, then there is a huge amount of difference between this, the traffic intensity.
A question.
Yep.
I believe it's relevant. Do they provide any open access to the data set? Is this, I mean, these people, are these from a lab or from?
They are from a lab, but probably they have a contract with an operator.
NDA? Yeah. Because this is very relevant to the project, I believe.
Yes.
And it may also be the case if we find it, I mean, important, that we ask them whether they can release this data traffic just only for use within Scavenge.
They say that you have this picture here already contacted.
You already did that.
Yeah, so they cannot release the data because they are not, there is an NDA, so there is no chance to have those data for us.
Okay.
So again, there are some restricted policies used by operator. So even in the paper, there are a lot of things that are missing. For example, there is no characterization of a user behavior. So you know about the aggregated, so there is no information about the different application, the different user behavior, how the user are moving across different zones. There is no information, probably because it is an information that has been restricted by the operator. And this is the reason why we, in our group, we decided to start this sniffing activity with TRIN, and we are disseminating our sniffers in different locations. So if you want to host one of our sniffers, you are free to ask to me, Trin, Lorenza, and we will provide all the information to install. Okay, so with this I end the part of the characterization of the two environmental variables that we have in energy sustainable mobile networks, the traffic and the energy arrival process. So what I want to introduce now is how we can control these two variables, the energy arrival and the load, with some intelligent control. So again, I'm referring here to an example with base station, because we are working on this, but you can change the base station with another device, and I think most of the things can be applied with a different modeling probably, but can be applied to different devices of the world system. So I put in this figure the energy harvesting base station. So we have solar panel, we have energy storage, we have the base station, of course, and there is this control entity that is deciding if the energy that is arriving from the solar panel has to be delivered to the load, or should be stored, or maybe should be sold to the power grid, or the other way around. We need more energy, and so we have to ask the power grid to give to us some more energy. Yes?
Is it a good approach to simply use the solar to the base station? Just direct, because I believe that it's better to store than use.
Yeah, whatever is a good, but the problem is that if you directly link this and you make no control, that you are relying on the fact that you have a given amount of hour where you have energy, and then the night you don't have energy. So, for example, there are some rural regions that are already deploying solar panels, but then they are realized most of the time with a diesel engine to have some more energy during the night in order to have energy for serving the user during low energy or night. So it's a different way of doing things, but we believe that including the energy storage can give to us more flexibility in managing and maybe to optimize something at the cost of an increase of the capital expenditures due to the price of the installation of the energy storage.
But I think his question was more like, should the energy source be routed through the storage and then to there should not be a direct link between the solar panel and the base station. Instead, it should always be routed through the kind of
Or it's more like
storage.
you charge the battery,
And
then you use.
then instead of a direct link.
Yeah,
the
sure,
solar-
sure. I mean, when I'm referring to this, I'm referring that the energy is going to the battery, and then the load is going to, I mean, the base station is taking the energy from the battery. Yes, yes. Maybe I didn't explain properly, but this was the idea. So the energy is going to the buffer, and then I refer to the energy in the buffer. Yeah. This is this was the question. Or not?
Yes, it was like a two option. You connect direct the solar to the base station, or it goes via the you store, then use. So either way.
Yeah.
I don't know.
Yeah.
I think it includes.
Yeah, I would say that again. In my vision, if I connect directly the solar with the base station, that I forced to use that energy when I have, and so that if there is no connection between the solar and the battery, how can I store the energy? So maybe I'm missing something, but there should be a connection between these two guys, or not?
That should be.
It could be, I mean, there is an inverter there, electronic inverter, which is taking care of adapting the load with respect to the energy storage, with respect to and then you're switching. It may be that the storage is full. In that case, it may be convenient to go direct, and then you're switching, and then you're adapting, and then you're pushing directly the energy from the panel to the antenna. That is also possible.
Yeah, sure.
This is what you do.
Yeah.
You do, but this is the energy manager there is sketched just to say that it's much more complex. You have electrical things,
This is just
switches, and some intelligence on top that is managing this.
You're right.
I have a question.
Yes.
So you should be for the hourly distribution of the sunlight and the sun energy, right? So I was wondering if you know about any references or models that translate those distribution, hourly distribution, daily distribution, into queuing models for the energy, like queuing queue of energy, or like the arrival distribution of energy.
What I know is that there are some models that are referring to Poisson process as an energy arrival process. This should be, for me, to be verified, as it is really something that is approaching the reality in a proper way. Because, I don't know, probably Poisson process is too simplistic, and it's okay for maybe some theoretical study and to define some bounds. But I'm not sure that is really the energy arrival process, for example, for a solar panel. This is my. I don't.
Hourly it changed a lot, right?
Yeah, exactly. So,
Maybe Poisson is very, very
or if you can change some variable in the Poisson process during the day, but I don't see any paper on this. So,
okay.
could be a good contribution, actually. Yeah.
You know about
Some question more? Okay, good in time. Okay, so I have to stay here, or I have to move this because I don't feel comfortable with all these things. It's okay if I move the mic? Okay. Okay, so I have to control this guy here. So I have to decide whether the energy should be delivered to the base station, to the energy storage, to the power grid, drain energy from the power grid. So in my opinion, this is a sequential decision-making process. So the idea is that I have an infinite horizon of time, and I can divide this horizon in slots, in decision slots, or decision instants. So for example, if I have at the instant k, I may want to take a decision in order to minimize a given cost function. But what I want also is that if I take this decision at the instant k, this decision is not having bad effect on the decision in the future. So the idea is that you have to have a trade-off between the present cost and the future expected cost. So what I want is to actually minimize a cost function over a given horizon of time, let's say capital T, so that, for example, this is the expression that we have. So this is the final cost function, and this is for the different decision instance that I have. And may occur also that is not completely predictable the cost that I want to minimize, so that in this case I can refer to the expected value of this cost function. And I may also want to have some constraints. For example, in our case, one constraint could be that the battery shouldn't be below a given threshold because of some restriction of the functioning of the battery itself. So in this case, we have this cost function, and we had some courses to solve these problems in the past school. And for example, one is using dynamic programming. And what I'm going to introduce now is some exercise that we did, some papers that we published together with Michele and Marco, that is exploiting dynamic programming in our scenario that we are studying. So for example, if we are referring to, in this paper, we take the Earth model, the traffic model from the Earth project, and we decide to change the size of the solar panel and the battery size for different types of base station, and try to understand which is the correct size that is going to achieve an outage, so that is lower than 1%. And we did this for different locations in the United States, for Chicago and for Los Angeles. So you can have, for example, in the case of Los Angeles, which is the more beneficial for us, is for a micro base station we have around 10 square meter and 80 ampere hour. So this is needed to have an outage of less than 1%. And for a pico base station, it has less power consumption model, that we have much less dimensions, so 0.8 and around 50 for the battery size. So these are a good starting point to understand the feasibility of our system, and which is the dimensions, which are the dimensions of the add-ons energy harvester that we have to put in our system. Okay. Yeah.
So in this analysis, you have considered like the spatio-temporal modeling through the data analytics.
Just temporal one.
Sorry.
Just the temporal model for the traffic. Then we, in the same paper, we have complicated a bit the things, and we have including also the different pricing model. We have this information because there are some available data set. Again, these are for an operator in the US. So we have in the gray color, you can look at this different price over different hour of the week. And then the idea is that at any decision instant, I may want to sell or buy a given amount of energy in order to maximize my profit, economical monetary profit. So the energy we say is negative when we have to buy the energy from the grid, and then I have a cost C. If the energy is positive, in the case I have a reward, which is actually proportional to the cost, but is discounted because normally when you sell the energy, the provider is not buying the energy at the same cost that is selling. So you have discount factor R here. And at each decision instant, I want to satisfy the full traffic demand that I have. So the idea is to maximize this reward here. And then again, through dynamic programming. Yesterday also we saw some details on these techniques. We can have some results, so I will show some results here to understand how it's working. This is the case for a microcell. So for example, in this case, A, B, and C, we are selling energy to the grid because we know that the harvesting process is good. So in these first 3 days of the week, we have a good harvesting process. So we have a good amount of energy to dispose with. And the price in this time of the day is high. So I decide to sell this amount of energy here, here, and here. In another case, in this case here, what I have is that the harvesting process is poor. So I don't have so much energy to dispose. In this case, what I'm doing is that I need to save my battery, and even I have to buy some electricity from the power grid in order to satisfy the demand for the next day when there is this poor energy arrival process. So what I'm saying here is that the control algorithm is flexible enough to take into account the variability of the traffic demands and the energy arrival process. And also, in this paper, we make this other calculation in order to understand, again, the feasibility of our solution. So what we are doing is that we are considering the cost function before, the cost of the energy when it's powered only by the grid, and the capital expenditure due to the installation of this new hardware. And we want to maximize the net profit over 10 years. 10 years because it's normally the life cycle of a base station. So we have two design philosophy here. The first one is to reduce the size of the battery and the panel, and the other one is to maximize the profit. So depending on the location, we have different monetary income after 10 years, and they are always positive. So what we are saying here is that this is really feasible and convenient for an operator to invest at the beginning of the life cycle of a base station with some additional energy harvester, because then it can have some profit at the end of the life cycle. So there is a return on the investment, and it can even earn some money at the end of the life cycle. Sure.
So this analysis is based on an optimization, right?
Yep.
And so to make it effective and to have this revenue, this income, you need actually, do you need to forecast the profile of the energy that you can harvest to make it effective for the future?
So what do you mean?
I say it another way.
Yeah.
Basically, to save money for the future, you need to optimize the system, right? So to know when to sell and when to keep energy, put it in the battery. So do you need the profile, the profile of the energy that you can actually harvest for the future to perform the optimization to make it effective for the future?
Yes, this is actually what we did in this. In this result, referring exactly to this optimization problem.
Yes, my question.
So we need this because since we need this, yeah. So the idea is here we are using dynamic programming, so we are making offline. So we know in advance all this information. So this is an estimation, it's not on the run, it's not online optimization. So we know in advance everything, we know the traffic in advance, and we are just making a feasibility study to understand how feasible it is in terms of economical terms, the idea to install these harvesters and battery in the base station. But probably with the next part, I will also discuss on the online part of.
Because I was wondering if one want to see if can use I don't know, the weather forecast to do it on.
Yeah, sure. Yeah.
An accurate forecast. Then you can.
Yeah, I mean, what I presented here is not the Bible. So the solar harvester is not the best one. The solar harvester model is not the best one. There are a lot of things that we didn't take into account when we build. For example, the battery is not taken into account. There's some inefficiency. There is no model there. Forecast, weather forecast, there is no weather forecast there. So, I mean, I encourage you to produce this kind of model because it would be really beneficial for us. So,
if I may add quickly,
sure.
what we want to do here, we take 20 years of solar data. So we assume that we have all the solar data in advance, written down, and we use that database by assuming that this is known. So we have an oracle or a genie that is already there and tells us for the future what's going to be. So we do.
So it's kind of bound.
We can put an upper bound of what we could possibly do, right? Of what we could possibly get, and then from here you can go online. And this is the whole scavenge project that has to devise online policies to somehow achieve energy savings with realistic models. As the forecast is way. Yeah, good question.
Yeah. So the final example that I have, and then now we are going to lunch, is about online optimization and is considering multi-cell scenario. So we are referring not only to one base station as in the previous cases, in the previous example, but in a HETNES scenario. So I have one macro layer and several small cells deployed in the same coverage area. And because of the previous results that we have in our previous study, we decided not to have solar add-ons in the macro base station, but only in the small base station. So we have solar panel plus battery here. And what we want to do is to maximize the use of the energy harvesters, so the offloading as much as we can to the smaller cell, again, in order to have satisfied the traffic demands. The control that I can have in this scenario that we decide to have in order to have another step is to also to have a direct control on the operation of the small cell, so we can decide to be on or off in a given point of time. And to make this, we had this problem. So how do we want to control these things? Centralized way or distributed way? It's a good question. There are some implications on both decisions. So in what I'm explaining next, I'm referring to distributed control, which doesn't mean that centralized control is not feasible. Actually, there are guys in this room that are studying centralized control there. So we can also refer to theirs. There are some implications because probably with centralized control, the complexity is exploding a bit. And maybe you cannot simply have an online optimization. You have to rely on offline optimization. So there are some constraints, but all the things are open to study. But now we are referring to distributed case. So in a distributed case, as Lorenzo already introduced this morning, we have agents that are distributed. So each small base station has a control agent that is controlling its behavior. This is the definition of a multi-agent system. It is a group of autonomous interacting entities that are sharing a common environment, in this case, the HETNET. And this environment is perceived by the agent as sensors, and they are acting on this environment as actuator. Okay? So what we would like to have is that the agents are programmed with some good behavior in advance, so a priori. In this case, could be perfect. So we program the agent, we forgot, and they will live forever. But the problem is that sometimes the system is really complex to be modeled and to be and to define a priori the behavior of the agent. And also the environment itself can change over time. So if I don't know and I cannot model statistically this changing over time of the environment, I cannot do a priori design or offline optimization. So in this case, what I may want is that the agent learn new behaviors online in order that the performance of the agent or the whole system is increasing gradually. So I have to drink something. So we already have some discussion this morning on this, but actually this distributed multi-agent system can be solved in a different way. So these are the three main areas of knowledge that are solving this kind of problem: direct policy search, game theory, and even reinforcement learning, temporal difference. And there are some intersection between these fields, so there are a bunch of algorithms that are referring to both theories, or to the three of those. Okay, so what I'm going to the example that I'm going to have is about multi-agent reinforcement learning. So we know very well reinforcement learning, so I'm not spend more time on this. What I want to stress here is just that I don't have a single agent, but I have multi-agent. So the main objective when I design an algorithm for a multi-agent reinforcement learning is that I have to achieve a stability or a convergence, even though there is no demonstration that in a multi-agent system convergence is obtained, but at least some stability I need to have. And then some adaptation, as I said before. So I need that the performance of the agent of the whole system are at least maintained or improved over the time. Otherwise, there is no change. I'm not learning. And then there are some challenges when I have to face with this multi-agent problem. Is that the first one is due to the complexity, actually. So the state action space could be very big. So there is a dimensionality problem there. Non-stationarity. The fact that I'm not going to have convergence for the whole system. And then another problem that I have to face is the coordination among the different agents of the system and the typical exploration trade-off that I have in all reinforcement learning algorithms. So the example is about distributed Q-learning. So we are following the distributed zone. So we have distributed self-organizing agent. And we want that each agent is learning on-off policy. So it autonomously decides when to be on and when to be off based on reinforcement learning, so to real-time interaction with the environment and based on the traffic demands and energy arrival that I have at the base station. So for this, we have to model the Markov decision process, so the state vector, the action set, and the reward. With the reward, we will update the Bellman equation. So you should know this equation very well. Since I'm referring to rewards, we are maximizing the reward. If I would use cost, then I would minimize. So it's maximization versus minimization problem. And what I have in this case is online optimization. Since each agent in distributed Q-learning is learning independently, we have local behavior or local policy, and we have a local Q tables or Q functions as introduced this morning by Lorenzo. And the problem is that each agent has only a partial view of the system. There is no a global vision of the system because he may have partial sensing of the environment that is interacting with. So in the case that I'm presenting here, we made this work with Marco, Lorenzo, and again with Michele. And we define this state vector. So we have the state that is composed by a variable that is the energy arrival, so the renewable energy that is coming, the battery level, and the load of the small base station. The action set is to be on or to be off. and a bit more of engineering has been done for the definition of the reward function. We have zero reward where the system in outage, so the battery is below a given threshold and we are dropping too many users. And then in the case that the small cell is on, what I want is to maximize the throughput, so to serve as many users as I can. And in the case that the small cell is off, what I want is to, let's say, charge the battery as fast as I can. Okay. And these are some performances. So what I want to present, apart from the numbers here, is the fact that when I have an online algorithm, what I have is that there is an initial phase in which things are not going good. So there is this stability problem. So this is the battery level. So as you may notice, the battery level is going below the design threshold many times until it reaches stability, and then it stabilizes and is not producing any system outage. So in that specific case, we see that since we are taking decision every hour, I mean, the system is not really quick. So we want to have some offline training. So we train the agent before putting in the environment. And in this case, we can have the initial Q table that are already in a stabilized form, and then we can exploit the starting point as a online algorithm. And then there are some things that I wanted to say to you about the behaviors of the small cell. When I have just one small cell in the coverage of a macro cell, what I have that in the night, actually, we have different months here. During the night, the small cell is most of the time off, and then during the day is on in order to offload the traffic from the macro cell and to fully exploit the renewable energy there. But also in some season of the year, so mainly in winter, so in January and April, no, just January in this case, I need some other sleep behavior during the early morning in order to save energy and to satisfy the traffic demand during the peak hours. In a multi-cell scenario, the behavior is more or less similar. The difference is that these values here are lower than this one. This is due to the fact that the base stations are kind of interleaving, so not all the base stations can be off at the same time, otherwise there will be a system outage. So they decide to interleave, and the time that they are off is less with respect to a single case scenario. And even in this case, we need some sleep behavior even in the early morning during summer again, because we need energy for this part of the peak, because otherwise there is no chance to serve all the users during the peak hours, because we have much more users, because we have much more base station. So, okay, some performance here. I will not go into the detail, just that we are beating here this algorithm, which is a greedy algorithm, which is switching off the base station just when the battery is off. But again, there are some work to do, because we don't have system performance that are good for an operator. So there are some optimization that we need to do in this field. And this is about the throughput gain, again, the same picture as before. But I want to spend some words on this graph, because we divide this performance. This is energy efficiency. We have a lot of discussion what is the energy efficiency, but let's say that in this case is the ratio between the throughput that I have in the network and the energy that is drained by the grid, so by the macro cell. And what I have is that we are comparing with this greedy algorithm that I described before, that during the winter period we are increasing a lot the energy efficiency of the system, but during winter we have less efficiency with respect to winter, and then we have also a decrease in behavior. So the main thing is that first, in summer we have much more energy. So even a simple algorithm, and as the greedy one is working quite well, let's say. And also there is another problem, is that the energy arrival process is so good that we are wasting energy. So there is no possibility to have energy stored in the buffer nor used for the base station to be fit. In fact, what we experience is that this is an average curve, is that during the hour of the day and during the day in the hour in the daylight, we have a lot of energy that cannot be stored nor used for the base station. So this again is giving us the possibility to use this energy for other purposes. For example, we can transfer this energy to the macro that is not supplied with energy supplier, with renewable energy supplier, and then to decrease again the energy drain from the grid, or we can sell the energy to the power grid in order to maximize our monetary profit. Okay, so with this I conclude the presentation. So I hope to concluding, what I wanted to say is that there is a parallelism between what we are doing in Scavenge with the use of renewable energy sources applied to mobile networks, and what the guy working on power grid are doing in order to enabling smart grids. So there are a lot of interaction. This is one of the reasons why we have this school here, when we have different projects from different research fields, because there are an intersection between. And also I presented some example of some optimization algorithm that we can apply for this kind of problem. So as I hope to have give some example for you to the application of the previous courses that we had in the previous schools, or dynamic programming, machine learning, convex optimization, to our environment and to our research field. Okay. Thank you.
Thank you, Paolo.